Alright friends, welcome back. In this video I'd like to go ahead and take a third day to talk about section P.2. There's just a lot of stuff in that section, so we want to make sure to kind of take it at an appropriate pace. And in this video we're specifically going to talk about rationalizing denominators, and then on the back side we're going to talk about a few extra topics, but we're going to go ahead and start here with rationalizing the denominator. So I want to talk about what that means, and then I want to spend some time in this video talking about how to go ahead and actually do it. So rationalizing the denominator, right? Basically, one of the things that we like to try to avoid in math is having any sort of radicals in the denominator of a fraction, okay? And the reason for that is because you may remember from elementary school that whenever you have fractions that say you want to add or subtract, like I'm just going to make up a couple of fractions here, like 2/3 plus 3/4, we would need to, in order to do this, find a common denominator. And here I believe that denominator would be, of course, 12. So in order to combine these two fractions, we would need to alter these denominators here by multiplying the top and the bottom by 4 in this case and by 3 in this case, so that we go ahead and say that this is going to be 8/12 plus 9/12, and of course adding those together we get 17/12 as our final answer. Again, that's more of an elementary school problem. But here's the deal. If your fractions have roots in them, that gets a little bit harder to do, right? So if you've got like something like a 1 over square root of 2 plus 3/4 or something like that, it's going to be a little bit more difficult to find the sum of these fractions here. And so one of the things that we would like to do is have a process that we can resort to where if we have a square root in the denominator, we can go ahead and get rid of it. And that's what this process of rationalizing the denominator is. It's a way for us to eliminate the root from the bottom so that we can go ahead and perform operations with these fractions in a little bit of an easier way. So you're going to rationalize the denominator if the denominator has a root in it, okay? And that could be a root with any index. We'll just say a nth root there. But anytime your denominator has a radical in the denominator, we want to go ahead and get rid of that. And this will go ahead and look like two different things here. So you will either have denominators that will have one term in them, or maybe denominators that have two terms in them. And depending on which case you've got, you might employ a different process here. But what I'd like to do first is go ahead and take a look at the case where we only have a single term in our denominator, okay? And so maybe let's go ahead and take a look at this first example here, and of course ignore the numbering here. We stole this from another resource. So here we have the square root of a fraction, right? The square root of 7 over k. And so the deal here is, again, if I wanted to take this fraction and add it or subtract it to another one, it'd be a little bit hard to do because this denominator is under the root. And so we're going to rationalize the denominator in order to get it out from underneath that root. Okay, and so here's how we're going to do that. We're going to pay attention to the index of the root, which here, of course, is a 2. And we're going to go ahead and play the same game that we did in the P.2 day 2 video, right? Where we were talking about how in order for, say, this k on the denominator to leave the root, we needed to have the same exponent, okay? And so the way we were kind of informally explaining that was, does k have enough money to leave the root, right? Well, here, of course, I don't believe that it does because this is simply just k to the first, and we need an exponent of 2 to leave the root, okay? And so here's how rationalizing the denominator is going to work when you only have a single term in your denominator like this. What you're going to do is, since it would take k squared to leave the root, we're going to introduce whatever is missing so that we could write this as k squared. Okay, so because this is just simply k to the first the way that it's written, we're going to go ahead and introduce to the denominator another times k to the first, because in the next line after this, we're going to be able to say I've got a root with an index of 2. If I introduce that extra k, then I'm going to have that k squared in the denominator, and then it's going to have enough money to leave the root, okay? So that's our strategy here. But the thing is, we can't introduce it to the denominator without also introducing it to the numerator to maintain our proportion here, okay? So I'm writing a lot of k to the firsts here, which just end up being a single copy of k. So we're just going to multiply the top and the bottom by k here, and that means that the numerator is going to change to 7k, and the idea is the same. Now our denominator is k squared, and that is enough money to leave the root, so I'm going to go ahead and write this so that k has left the root, so there's no more root in the denominator. But in the numerator, I still am left with 7k because those guys didn't have enough money to leave the root. And this is going to be our result here, okay? So this is equivalent to what we started with, but it is rewritten in such a way where we don't have the denominator underneath the root, and we don't have any other extra roots in the denominator itself. So that process is called rationalizing the denominator, and the idea is simple. You want to introduce whatever it's going to take to let the denominator have enough money to leave the root. Okay, so let's see another example of that. So here in the next one, right, now we have a fifth root, all right? And so our denominator, it looks like I have y to the second power, which is not quite enough money to leave the root. What we would need this to be is a 5 in order to match the 5 on the index of our root in order to leave, right? Well, it's not quite that, but we can go ahead and start introducing more copies to the denominator, okay? Specifically here, it would take 3 more copies in order for it to get up to a y to the 5th here. So I'll go ahead and write that here in my next line. This would be the 5th root of something over y to the 5th if we do that. Remember, if we multiply like bases, we would add those exponents. And so that really would be y to the 5th. But remember, what we said before is you can't introduce it to the bottom without also introducing it to the top. And so we're going to go ahead and make sure to introduce that to the top as well. So our numerator becomes 2xy to the 3rd whenever we do that. And again, the whole point of that was that now y has enough money to leave the root. And so I'll go ahead and say that that has enough to leave the root. So we'll circle that, and we'll rewrite this as the numerator is still under the root. And remember, that's a 5th root, so we're going to keep track of our index, 2xy to the 3rd on top. But now on bottom, because that y has enough money to leave the root, we're just going to go ahead and write our denominator of y without a root next to it. And again, because that is a denominator without a radical in it, and it's not also underneath the radical itself, we are going to go ahead and call that good. That is rationalizing the denominator. Where this is going to start to get difficult is when there are many terms underneath the root. And so here in this next example, I just want to do what we did in the last video and just kind of keep track of all the different types of terms that we have underneath our root, right? And so here we're going to start off, it looks like our index is 4, and it looks like we're going to start off here with an x, and it does not look like it has enough money to leave the root. Right now, it just has an exponent of 1. We need an exponent of 4 to leave the root, so x is going to stay underneath for the time being, okay? Move on to this y term. It looks like it has an exponent of 2. Not quite enough money to leave the root, so we're going to keep that underneath. And if you look at this z term, it looks like that's z to the 11th, and that has a lot of money to leave the root, right? So we could break up this z to the 11th just like we did in the last video. If you need a refresher on that, make sure to watch that. But we could break this up as z to the 4th times z to the 4th times z to the 3rd is what would be remaining there. And again, the reason we might write it like that is because this z has enough money to leave the root, and so does this one. Those are both written so that they have exponents of 4, and that is enough money to leave the root. However, that z to the 3rd does not have enough money to leave, so we're going to keep that under the root. Okay, so when we go ahead and write here our next step, all the things that are able to leave the root are going to be written out front, and everything that is remaining is going to stay under the roots here. So that's 2 copies of z. So instead of writing something like z times z on the outside, we're going to go ahead and write that as z squared. Okay? And so now I have my 4th root of everything that had to stay underneath. So I've got my x, I've got my y to the 2nd, and then I've got my remaining z to the 3rd that was under the root there. Okay? Now, I'm not going to go ahead and write the top of my root just yet, because we're now going to go ahead and move on to the next part of this, which was we are going to now go ahead and the way we kind of described this in class was we're going to dole out some loans, okay? Because what I mean by that is if you look at x here, remember that its exponent is 1. We really need it to have an exponent of 4 so that it has enough money to leave the root. And so the way that we're going to go ahead and describe that is we're going to introduce a number of copies of x here so that it is allowed to leave the root. So if it already has an exponent of 1, I need it to get up to 4, so that means I'm going to go ahead and introduce 3 more to the problem, okay? So we're going to keep track of that, right? Moving on to my next type of term, it looks like I now have a y to the 2nd term, and it's not quite 4, but we can get it up to 4 if we dole out a loan, right? We're going to loan this y term an additional 2 y's so that we can get up to 4, okay? And it's the same thing with that z, okay? So we have z to the 3rd power here, and we are going to go ahead and dole out a loan here so that we can get up to 4 so that that z can leave the root. And so that is going to be just a single copy of z. It's already got 3, so we just need a single copy more to introduce there, okay? Now, to be very clear with what we're doing, we are doling out these loans under the root. Okay, so if you look at what we are introducing here, we are introducing some new x's and y's and z's, but these are going to be under the root there. So what that means is we're going to have to be a little bit careful whenever we make sure to keep things proportional by introducing stuff to the top. Okay, and this is probably one of the more difficult concepts of the entire video, so I really want to make sure that we're paying attention on this, right? So this stuff right here was already under the root. What we introduced to the problem was this stuff right here. These are the loans that we doled out. So we have to make sure to also introduce them into the numerator, but because we introduced them under the 4th root in the bottom, we're going to have to introduce them under a 4th root in the top. Okay, and so here's where I'm going to go ahead and write all the loans that I doled out. So I had an x to the 3 that I doled out. I had an x to the, or sorry, not x, y to the 2nd that I doled out. And then finally, I had that extra copy of z that I doled out there too, right? So again, if I introduce those loans under the 4th root in the denominator, I'm going to also have to introduce them under a 4th root in the numerator, okay? And again, don't forget the whole point of this, right? So the whole point was so that we could rewrite our x, y, and z under our root as having the appropriate amount of money to be able to leave that root. So I've still got this z to the 2nd power there, and I've got a 4th root. And by doing that, remember, x now has 4 copies. That's enough to leave the root. Y also has 4 copies. That's enough to leave the root. And z also has 4 copies. That is enough to leave the root as well. So again, if we were kind of going off of what we did in the last video, now we have enough money to leave the root for x, y, and z. So I might go through and just kind of circle these guys here. They now have enough money to leave the root. It took $4. Each one of these guys has $4 now because of those loans that we doled out. And then the top part, there's really nothing to do to simplify that, so we're just going to go ahead and write there 4 times the 4th root of x to the 3rd, y to the 2nd, z. Okay? So now, cleaning up that denominator, if everything is allowed to leave the root now, let's go ahead and just keep a running track of what left the root. So I have a single copy of x that left. I have a single copy of y that left. But be careful here, because whenever you look at these z's, right, we had a z to the 2nd power that was already in front, and now we're introducing another z out to the front as well. So that's going to be 3 total copies of z there. So we're going to say z to the 3rd power, okay? And then we're going to, of course, write that underneath 4 to the, or sorry, not 4 to any power. We're going to write 4 times the 4th root of x to the 3rd, y to the 2nd, z. Okay? So again, that is a complete process of rationalizing the denominator, because now we have written our results so that we don't see any radicals at all, and also the denominator is not stuck underneath a root. Okay? So let's go ahead and try that process one more time. It's going to be a little bit of a longer video, but remember, you can always fast forward through it. You can always pause and rewind and do all that fun stuff, right? So if you have a longer video, always remember that you can fast forward through it. But here in the next example here, I just want to demonstrate that process one more time. I've got a copy of 2 here, and then I'm going to just basically devote all the different types of terms I have to a different color under my root here. So we'll just go ahead and do that here really quick. And then notice that the number of dollars that you need to leave this root is 3. Okay, so maybe let's go through real quick and identify what has enough money to leave already, okay? It doesn't look like 2 has enough money to leave. It doesn't look like your x term has enough money to leave, but it does straight away look like y does have enough money to leave. And then if we break up our z term, we could break that up into z to the 3rd times z. It will then look like this z has enough money to leave the root on its own, okay? So we'll go ahead and make a note of that, and then in the next line we'll say everything that gets to leave the root, that was a copy of y and a copy of z, and then everything else has to stay underneath that cube root there. So that was 2 and x squared, and then a single copy of z. All right? So that's just us doing what we did in the last video, simplifying that root. Okay? Now we get to look at the radicand that we have now, and we're going to look at each part of it again, so I'm going to stick with my colors. And we're going to go ahead and dole out some loans so that each of these guys have enough money to leave the root. Okay, so basically whatever it's missing to get up to 3 copies, or $3, however you want to think about it, we are going to introduce that, okay? So it looks like 2, that's just 2 to the first. So it only has $1 at this point. So we're going to go ahead and introduce 2 more to bring its exponent up to 3. So that'll be 2 to the second power that we introduce, okay? For that x, we did that in green, so let me switch to green here. It looks like it already has 2 copies, and we need to get it up to 3, so that's just going to take an additional copy of x to get it up to 3. And then finally, for that z term there, it looks like it's z to the first power, so we just need to introduce another 2 copies of z so that it gets to leave the root, okay? And remember, when we dole out these loans, this is all underneath that cube root, so that when we go to the numerator, we're going to have to introduce that cube root. And I've got my ink to shape tool on, so that's why my writing is doing a bunch of weird things there. We're going to have to introduce those, right? So we introduced the cube root of 2 to the second, and then x, and then z to the second. Remember, these are the loans that I doled out in the denominator underneath that cube root, okay? So we're going to keep track of everything. So when we write our next line here, in the denominator, we're going to have the following, right? We already had the y and the z from out front. But now we have the cube root of, taking a look, we've got our 2's, right? We brought the 2 up to a power of 3, so we'll say that, 2 to the third. And then we brought our x up to the power of 3, so we'll say x to the third. And finally our z, we brought that up to the power of 3, so we'll say z to the third. Okay, just doing this nice and slow so that we don't lose anybody. And then in the top, since this is just a 1 times right here, there's really no need to write it. So I'm just going to go ahead and write the cube root of 2 to the second power that I had in blue up there. I'm just going to go ahead and write that as 4, and then x, and then z to the second. Okay? And again, the whole reason for us introducing those loans is because it takes $3 to leave, and now we have each one of these guys having the right amount of money to leave the root. Okay? And so now we're going to go ahead and write our final result here. A 2 can leave the root. An x can leave the root. There was already the y out in front of the root. And then remember, since we already had a copy of z out front, and we're saying that another copy of z is going to leave the root and be out front, that's 2 copies of z total. So we're going to say z squared. All right? And then on top, we just have the cube root of 4xz squared. Okay? And that is going to be our final result for how to rationalize that denominator. So again, you know you're finished when the denominator has left the root entirely and if your denominator doesn't have any roots in it whatsoever. Okay, that's how we know we're finished there. So I hope that makes sense to you. Please feel free to let me know if it doesn't. We can go ahead and continue to work with this. But our next couple of examples are going to involve this idea of a 2-term denominator. Okay, and so there's a go ahead and handle how to rationalize if we have a 2-term denominator, and it's going to be by multiplying times this. It's something called the conjugate, okay? And so what a conjugate is, we'll go ahead and write out some examples of conjugates, right? So what a conjugate is here is basically an expression like, maybe I'll come up with a random example from off the top of my head. What if I had like 2 plus the square root of 3, okay? If I want to find the conjugate of that, I'm going to write that same expression, but instead of the plus, I'm going to write the opposite of plus, or the inverse operation to addition, which is subtraction, okay? So in general, if you guys have an expression of the form like, say, a plus b times the square root of m, something like that, if that's the form that we fit, then the conjugate of it is going to be that same expression, but instead of a plus, you're going to have a minus, okay? And there's a reason why we would want to introduce the conjugate, and we'll explain that as we go through an example. So let's take a look at the next one here. That's going to be number 28 here. And look at the bottom, right? It looks like that is a 2-term denominator. And so what we're going to do to figure this out, or to rationalize the denominator, is we're going to introduce the conjugate of that expression to the denominator. So if it already said 1 plus the square root of 2, we're going to introduce 1 minus the square root of 2. And whatever we do to the bottom, remember we also have to do to the top, so we're going to go ahead and write here times the expression 1 minus the square root of 2. Okay? Now I want to dive a little bit into why that is. All right? So why would we introduce the conjugate here? Okay? Well, I'm going to see if you remember your Algebra 2. What we've just introduced here is in the denominator, so maybe just kind of scroll this down so we're focusing on just the denominator for the time being. What we've just introduced is something that looks an awful lot like this form, right? Maybe something that's a little bit reminiscent from something you learned in Algebra 2. U plus V times U minus V, okay? Maybe that looks a little bit familiar to you. Maybe you don't quite remember what we called this, but this was one of your special product formulas from back in Algebra 2. We always said that if you have an expression that looks like this, where you have U plus V times U minus V, what this was always equal to was an expression that looks like this, right? U squared minus V squared, all right? And that is something that we called your difference of squares formula from Algebra 2. Again, basic idea is if you have something that looks like this, then it's always equal to this right here. Okay, and that's really handy because that prevents us from having to do a whole bunch of work trying to FOIL this out and simplify our denominator and that kind of thing. We could just go ahead and simply apply this formula and we're good to go. So the only thing that we really need to figure out is what's playing the role of U and what's playing the role of V in our example. Well, if you look closely, playing the role of U, that's just going to be 1. So following this formula here, I'm just going to say U squared over here, or 1 squared, okay? And then playing the role of V, if you look closely, that's just going to simply be the square root of 2. And so I'm going to go ahead and write that square root of 2 squared. Okay? Now, why does that help? Well, I mean, it certainly looks a little bit more clean, but the reason that this helps ultimately is because if you think about what it is we just wrote, that's 1 squared, which is just 1, and then minus the square root of 2 squared. Remember that this index on this root is a 2, and we're squaring that. So remember from one of the last videos that if we are having the same exponent as we do the index of our root, those are inverse operations and they undo each other, just leaving us with the radicand, and here that's going to be 2. So what are we saying? Are we saying that this denominator is just as simple as just 1 minus 2? Well, absolutely, yes, we are. We're simply saying that the denominator is just going to be 1 minus 2, which is going to turn out to be negative 1, okay? But that's our denominator. Let's take another look at our numerator, right? When we introduce the conjugate to the numerator, we're going to have this factor of 3 times the expression 1 minus the square root of 2. And my recommendation to you is to just go ahead and leave that factored. Don't distribute in that 3, because watch what happens, right? When we go ahead and continue with our work here, copying that in our next line, and then finally in our last line, one of the things that I want you to notice is that we can go ahead and figure out what 3 divided by negative 1 is. And of course, that's just going to simply be negative 3 here. So our final result we can write as 3 times the quantity 1 minus the square root of 2. And this might even look like something that doesn't even have any denominator at all. And that's oftentimes going to happen, especially when your denominator turns out to be something that works well with what you have in the numerator. Okay? So we don't have any denominator at all anymore, meaning that we have rationalized our denominator. So this formula right here, again, this is something that we call the difference of 2 squares. Okay, so I'll just abbreviate here, the difference of 2 squares. All right, so you may want to write that in your notes somewhere so you don't forget. Whenever you introduce the conjugate, you're forcing that situation to be a thing, and then we can make this formula kick in. Okay, so let's try that one more time here. Example number 29. It already says 4 minus the square root of 2. So we'll just do one really quickly, assuming my computer will let me erase what I just wrote and switch to my blue pen here. We already have 4 minus the square root of 2. So we're going to introduce the conjugate of that. That will look like 4 plus the square root of 2. Okay, and again, whatever you introduce to the bottom, you have to introduce to the top. So we're going to introduce that to the top as well. But again, what you have just forced here is a difference of squares scenario, okay? We have something that looks an awful lot like U minus V times U plus V. And so we're going to go ahead and just simply apply the formula. Playing the role of U today is simply just 4, so we're going to say 4 squared. And then we're going to subtract off whatsoever is playing the role of V squared. Well, here, that's just another square root of 2, and I'm hoping that you're kind of catching on now that the reason why we do this is so that we can get this nice formula that has that nice exponent of 2 in it so that we can cancel out with our square roots. So if I'm just going to write the square root of 2 squared, those are going to cancel out, just leaving me with 2. Okay? And then in the numerator, I'm going to have that factor of square root of 3 times that expression 4 times the square root of 2. Okay? And so now you'll notice that our denominator does not have any roots or radicals in it whatsoever. Matter of fact, you might be able to figure out what that number is mentally, since 4 squared is 16, take away 2, that's just going to be 14. So we're going to have square root of 3 times the expression 4 times the square root of 2 in the top. and this is all going to be over a value of 14. No roots in the denominator. Our denominator is not stuck under a root, so we have truly rationalized our denominator here, and that is a complete problem. So whenever you're rationalizing the denominator in general, regardless if you have a one-term or a two-term denominator, you're always going to follow that process. If it's a one-term denominator, you're going to be doling out loans so that you can get the exponent to match the index of the root so stuff can leave. If you've got a two-term denominator, you're going to introduce the conjugate to both the top and the bottom to force a difference of squares scenario so that you can apply that formula, and then things simplify down in a nice way. Okay? So we're going to go ahead and move on to the next little part of this set of notes, which is how to perform operations with radicals. Okay? And so a little bit of a two-step process here. It says the first thing we need to do is make sure to simplify all the radicals that we can. That is from the last video, day 2 of P.2. But then after that, we're going to combine radicals. So we're going to start to add and subtract radicals depending on what we see in the problem. And there's something you need to check for before you have the green light to combine radicals, and it's this right here. You really need to make sure, it says in the second step, if the radicals have the same index and the same radicand, that gives you the green light to go ahead and combine radicals, okay? So that's going to be something that we're going to need to look for here in the next couple of examples, right? So here we have this big, long expression. It involves a bunch of roots of numbers here. So the first thing that we always need to check to make sure that we do is simplify the radicals. So here we have a bunch of square roots where the index is a 2, of course. And here underneath the radicals, it looks like 3 and 3 and 2. These are all just to the exponent of 1, and that's not enough money to leave the root. So we can't go ahead and simplify those roots any further. But what we can do is notice that we have a couple of radicals here that do have the same index and the same radicand, namely these first two, okay? So you'll notice that they both have an index of 2, and they both have a radicand of 3, okay? So I want us to be also very clear about what we're saying here as well. Whenever we go ahead and add them together, what does that really mean? Well, that means I'm adding 2 of these square roots of 3 plus 4 of these square roots of 3, okay? So 2 plus 4, that of course is going to mean I have 6 of them. 6 square roots of 3. And you notice there that I didn't really do any sort of arithmetic with the indices at all. I didn't do any sort of like adding of the radicands or whatsoever. I just kept it as the square root of 3 because that's the thinking process that we go through. We have 2 of them, we added 4 more, and that means we have 6 of them total. Okay? Now, the only question left is what is there to do with this radical that is at the very end? The best that we could do there is just say that that is not going to be a like term with the first one that we had. And so the best we could do is just go ahead and write this as an expression in that way, where we can't combine those. Remember, we can only combine the roots if they have the same index and the same radicand. Here, those radicands are different. One is a 3, the other is a 2. Okay? So that's a complete problem on that one. On this next one, again, we're looking for our radicals to have the same index, the same radicand. I think we are already set to go here in this first example. They both have an index of 2. They both have a radicand of 5. So don't forget what we're going to say here, right? We're going to add these together. We're going to take 4 of those square roots of 5 and add on 3 square roots of 5. That's going to make a total of 7 square roots of 5. And then, of course, there's that big minus 5 there at the end. Again, that is not going to be a like term with what we've got already. And so we're just going to go ahead and box that as our final result in that way. So super simple, okay? The only time that this is going to get a little bit more challenging is if you guys have radicands that I give you straight up that do not look like they match. And here that's an example of that. So what we would want to do here is we would want to go ahead and follow that process that we discussed in the previous video where we are breaking up that number underneath the radical into perfect square times something left over, right? And so let's go ahead and do that here. How would we break up a 48? Well, we may need to look at that list of all of the perfect squares, figure out what the largest perfect square is that goes into 48. I believe that's going to be a 16. And so I could rewrite that 48 as 16 times 3. And the reason that I might want to do that is because 14 can be written as 4 squared, whereas 3 is going to have to stay the same. And so remember the thinking from the last video, right? The index on this root is a 2. And so what that's going to mean for us is that anything that has $2 can leave the root. And here that is going to be 4 that is able to leave the root. And we'll deal with that here in a second. Let's talk about this 27. Okay, so same thing. We're going to break this up as a perfect square times some leftovers. I think the largest perfect square that goes into 27, of course, is 9. And we can go ahead and write that as 9 times 3. And of course, that 9 we could write as 3 squared, whereas that remaining factor of 3 there is going to stay 3. And again, the thinking is the exact same. If I have an exponent inside with the same number or value as the index of the root, then that is something that gets to leave the root, and we'll write that on the outside, okay? So when we write our next line here, the only thing that we got to be a little bit careful of is the fact that we've already got this 2 and this 3 on the outside of our roots. And we're saying that this 4 and this 3 from the inside are going to move to the outside. So the way we handle that is we are going to go ahead and write that 2 that was already there, but now we're going to say that a 4 has left the root, and that's just going to be simple multiplication, okay? That what has stayed under the root is a copy of 3 there, and then we have a big minus sign. A copy of 3 was already outside the root. We're saying that a copy of 3 is going to leave this root, and that's going to leave behind a copy of 3 under the root. Okay, and so that kind of begs the question, well, how do we continue here? Well, all we're going to have to do is multiply the numbers that show up in front of the roots here, which is very simply done. That is just going to simply be an 8 on that one and a 9 on this one. And so when we write our next step, this is 8 square roots of 3 minus 9 square roots of 3. And again, the thinking is the same, right? We're going to perform a subtraction. We have 8 of these things, and we take away 9 of them. And so our final answer is going to be 8 minus 9. That means negative 1. And so negative 1 square root of 3, that could be one way that we write our final answer, but the more simple way would be to just simply write negative square root of 3 as our final result for that. Okay? And so that is going to be a complete problem there. All right? So if your radicals are not already simplified, like how we talked about in the last video, that's going to have to be something that we do to start that problem off. I'm going to go ahead and skip that next one, and I'm going to go right into our next and last final topic, which is simplify using your properties, right? So here, instead of adding or subtracting 2 roots, here we are now multiplying 2 roots, okay? And the easiest way to go ahead and do this is to use 2 of your exponent properties that we learned about in the last video. And so I want to write them up here at the top so that we can reference them. One of the radical properties that we saw in the last video was that if you were to take the nth root of some base number a to the mth power, then we can go ahead and write this as a rational exponent by saying the base number a to the power of m over n. Okay, and when we described this property in the last video, we said that the index of the root is always going to be the number that's on bottom, so make sure not to forget that, right? So this is one of the properties that we're going to borrow for this work right here, so we'll keep that up at the top. And the other property that we're going to need is if I have the same base but different exponents, we need to remember what we do with those exponents, right? In this case, we would just go ahead and add those exponents and write a new base of a there, okay? So it's going to be these properties of radicals that we're going to need in order to go ahead and figure out how to multiply 2 roots together, and I'll show you how that works here, right? Basically, the first step is we are going to convert all of the radicals that we see to a rational exponent by using that first property, okay? So that's going to be the first thing that we do for number 34 here, all right? This is an index of 2, and that's an index of 3, so when we write these using rational exponents, that's going to be x to the power of 1/2 as that first one, times x to the power of 1/3 as that second one, okay? Again, remembering that the index of the root is the number that's on bottom of those fractions. And that's us using that first property, okay? What we're going to do then is we're going to use the second property, where we're saying that if we multiply like bases, then we add those exponents. And here our like bases are both x, and so this is going to be x to the power of 1/2 plus 1/3, whatever that is, okay? Now, you may need to use a calculator, or maybe you're good at adding fractions in your head mentally, but this is going to be x to the power of, I believe that is going to be 5/6, okay? So I'm not going to get too bogged down in this video with explaining how to add 2 fractions together. You would need a common denominator for that. But that would be the way to go ahead and write our final result using rational exponents. I want us to go ahead and follow this general rule in class, though, of if I gave you the problem using radicals, I want you to write your final result using radicals, okay? And so the way to convert what we've got here to a radical is just, again, using that first property from up at the top there. If what I've got is x to the power of 5/6, remember that the number on bottom is the index of our root. That would be the 6th root of x to the 5th. And that will be our solution for this problem here, okay? So again, following that general guideline, if I give you the problem using radicals, I'd like you to end the problem using radicals. I'm going to go ahead and skip that next one, and I'm going to go right to number 36 just for the sake of time in the video here. I know it's getting a bit long, but let's go ahead and continue and see what we were going to have, right? So on this very last example, we've got a bunch of bases of x, right? So again, this is exactly like what we did in your exponents lesson, okay? I believe that was P.2, day 1. Okay, I might just look at the numerator here and see that I've got like bases of x, and so we remember that if I have like bases of x that I am multiplying together, which we are here, then we're going to go ahead and add those exponents together. So that'll be -2 plus 1/3. That'll be the exponent on x in the top. On the bottom, I've just simply got 2 times x to the power of 2/3. We'll hold on to that for the time being as we figure out what this is going to add to in the top. And again, it might be something that you need the calculator for, maybe not. But if you figure out what that's going to be, that is just going to simply be -5/3. Okay, so we're going to go ahead and write that as x to the power of -5/3. If you guys need assistance in the calculator, then please let me know. But that would be something I would expect you guys to be able to do at this point. And now we're almost finished, but remember that whenever we have a negative exponent, remember that that negative exponent has a single job. That job is to swap that base of x down to the other side of that fraction bar, okay? And so what we have here now is we have the x to the 2/3 that was already there in the bottom, and then whenever that we have that negative exponent, that flips the x to the 5/3 down to the bottom as well. So if I've got x to the 2/3 in the bottom, and I flip down that x to the 5/3, well, it looks like in the bottom here, I have like bases of x that I'm multiplying, so I would have to add those exponents there, okay? So that would simply be x to the power of 2/3 plus 5/3, and that would be finally x to the power of 7/3 there for us. So we're going to write our final result. We're only going to have a factor of 1 left in the top, and then that is going to be our factor of 2 that was left over, and then finally x to the power of 7/3, and that will complete the problem, okay? So, again, making sure to leave my final result with rational exponents if the original problem was given to me using rational exponents. So I know it was a long video, guys. I apologize about the length, but there was just certainly a lot to talk about here in this video, so please feel free to go back and watch certain parts if you need to. Let me know if you guys have any questions whatsoever, but that's all I've got in this one. Thank you very much for your attention, and I will speak with you all in the next one.